Good morning, students. So, in continuation of the previous video, dear students, today we will discuss one of the application of dimensional analysis is to check the dimensional consistency of a given physical relation. Means if a physical relationship is given to you, suppose I am stating that if you are given with a physical relationship that is V is equal to U plus AP, then you have to check that whatever the dimension in left hand side, dimension of left hand side must be equal to the dimension of right hand side, and if both the dimensions are going to be equal, then the given physical relation is dimensionally consistent. Means dimensionally the given physical relation is correct, but it is not necessary that the physical relationship which are dimensionally correct is physically correct also. So these things we will discuss in this discussion under this topic. So let us suppose first of all we explain the principle of homogeneity, because this thing is based on the principle of homogeneity. Principle of homogeneity. Principle of homogeneity. And what does this principle explains? Dimension of each term of the physical relation dimension of each term of the physical relation on both sides of the equation must be same. And according to this relation we can say that mass is added or subtracted with mass only. Mass is added and subtracted with mass only, length is added and subtracted with length only, and time is added and subtracted with time only. So this is all about the principle of homogeneity, and based on this principle of homogeneity, it is clear that from the definition, each term of the physical relationship, whatever the physical relationship you have, each term of the physical relationship on both sides of the equation becomes same. Means in left hand side and right hand side whatever the terms are there, and if their dimensions are same, then that physical equation, that physical relation is obeying the principle of homogeneity and it is dimensionally correct. So we are going to take an example, and on the basis of that example we are telling the principle of homogeneity. Means we are saying the dimensional consistency on the basis of principle of homogeneity. So we are taking a formula. Suppose we are taking the formula F is equal to mv square upon r square. Here the left hand side it has dimensional formula for F, and its dimensional formula is m lt minus 2. Now on right hand side that is equal to m v square upon r square, and it is equal to what? Mass m lt minus 1 whole square and upon l square. Clear? And it will give us m l square t minus 2 upon l square, and from here we get the value mt minus 2. mt minus 2. What you are saying that whatever the dimensional formula in the left hand side is not equal to right hand side. So the above relation is dimensionally incorrect. And if it is dimensionally incorrect, then it is physically not consistent. This relation is physically also unfit and dimensionally also unfit. Not physically and dimensionally not correct. Now the second relationship, second example we are taking. Second example we are taking B, and it is equal to S is equal to UT minus half AT square. So we are checking it dimensionally. We are checking it. This is LHS, and in LHS side, dimensional formula for S is equal to L. And RHS side, that is half AT square, and that is equal to L t minus 2 and t square, and from here it is equal to L. Now you are observing that dimensionally it is correct. The above equation is dimensions LHS is equal to RHS. So dimensionally correct. It is dimensionally correct. But it is not retardation here given, it is acceleration given here. So physically it is incorrect. Because physically our formula for acceleration, the formula is S is equal to UT plus half AT square. So physically it is unfit. This formula is physically dimensionally correct but physically unfit, because the actual formula is S is equal to UT plus half AT square. Now third one is time period for simple pendulum, MGL, under root I upon MGL. C is equal to time period T is equal to 2 pi under root I upon MGL, where I is the moment of inertia, T is the time, L is the length, G is the acceleration due to gravity, and M is the mass. So we are checking it dimensionally. For dimensionally, LHS T, time period T, dimension of time is T, and it is equal to LHS. Now RHS, for RHS under root I upon MGL. you can write it as m l square, and then m l t minus 2 here, and from here what you are getting, m to m cancel out, l square cancel out, t minus 2 to under root t square, and it is also equal to t. So here you are seeing that L dimensionally LHS is equal to RHS. So it is dimensionally correct, and physically correct also. Dimensionally correct as well as physically correct. So by this application of dimensional formula, we can ensure that okay, the given physical relation is dimensionally correct or incorrect. Mere the dimensional correctness of an equation does not ensure its physical correctness. As I have told you, कि physical correctness is not fulfilled only due to the dimensional consistency. For example, work and torque. Torque is equal to force into perpendicular distance, and work is ml square t minus 2, and torque is also ml square t minus 2. For example, one more example, I am discussing work and torque. Work and torque. Dimensional formula for work, that is equal to ml square t minus 2. And for torque also, the dimensional formula is ml square t minus 2. This is force into distance, force into perpendicular distance. Both dimensionally same. Both are dimensionally same, but physically they are not same. Or it is called as physically absurd. They are called as physically absurd or physically not same. So dimensional correctness does not mean that physically they are correct. Now, the fifth application of dimensional analysis. Fifth application of dimensional analysis. Fifth application of dimensional analysis. The fifth application of dimensional analysis as a research tool. As a research tool to derive new relation. As a research tool to derive new relation. Means this dimensional analysis can be used as a tool, as a device, as a tool to derive new relations. Means suppose I am saying that we are given with any physical quantity dependency on other quantities. From that dependency we can easily find out the relationship between the physical quantities, and that is what we are saying as a research to derive new relation. So I am explaining it by taking an example. Einstein mass energy relation. Einstein mass energy Einstein mass energy relation. It says that when mass of a body is going to be converted into energy, the energy so produced depends upon the mass and the velocity. Means when mass of the body is going to be converted into energy, the energy so produced depends upon mass and the velocity. So from this conclusion, we are finding out the relationship between energy and mass. Einstein mass energy, what is the relationship between energy and mass? So look at here. As from the statement, it is clear that energy is the function of mass into velocity of light. Means energy depends upon the mass and velocity. So energy can be written as K constant m to the power x c to the power y, where K is dimensionless constant. Now energy m L square t minus 2 is equal to K m x this is mass, the mass dimension from mass m, and C L t minus 1 y, and from here m L square t minus 2 is equal to K m per x L y t minus y. Now by principle of homogeneity, we have to find the value of x and y. From the principle of homogeneity, we have to find out the value of x and y. So from principle of homogeneity, from principle of homogeneity, look at here. If we are comparing the dimensions of mass, length and time, then what you are getting, x is equal to 1 and y is equal to 2. M is equal to 1 and y is equal to 2. Now putting the values of x and y in the relationship. So E is equal to K m per c square, and you can write it as kmc square. Experimentally, by experiment K is considered as 1. By experiment K is considered as 1. So the relationship energy is equal to E is equal to mc. This is the Einstein mass energy relationship. The second concept is Stokes law. The Stokes law. The Stokes law depends upon the viscosity or opposing force produced on a bob which is falling inside a viscous fluid, and on what factors the opposing force or driving force or viscous force which is experienced by a bob which is falling inside a viscous fluid, on what factors it is going to depend. On the basis of that, we will derive the formula for that force which is experienced by the bob when the bob is going to fall down in a viscous fluid. The next is Stokes law. Stokes law. What is the Stokes law? That is the driving force. You will study quite in detail in the fluid mechanics. I am showing here. The driving force is the function of viscosity R and V. Eta is the viscosity, coefficient of viscosity. R is the radius of the bob and V is the velocity. So F is equal to constant K eta x R y V z. Now this force M L T minus 2 is equal to M L minus 1 T minus 1 power x power y L T minus 1 power z, or M L T minus 2, which is equal to M power x L minus x plus y plus z T minus x minus z. From here, x is equal to 1 minus x plus y plus z is equal to 1, and minus x minus z is equal to minus 2. And on solving for x, y and z, on solving it for x, y and z, we will get the values x is equal to y is equal to z, that is equal to 1. All the values are equal to 1. And now putting these values in equation 1, we get f is equal to k eta r v. And by experimentally we can find the value of k is equal to 6 pi. Experimentally k is equal to 6 pi, that is the constant. So the driving force is equal to 6 pi eta r v. This is the driving force. Now the third one is Planck's length. Planck's length. Third one is Planck's length. Planck's length, and this Planck's length is denoted by QL. Now Planck's length can be given by QL is the function of gravitational constant, velocity, and Planck's constant H. So it can be written as L, that is Planck's length, K, G, X, C, Y, H, J. On these factors, they are depending. So L is equal to m minus 1 L cube t minus 2 power x L t minus 1 power y and m L square t minus 1 power z. And from here L is equal to m minus x plus z minus x plus z. L 3x plus y plus 2z. Am I right? And t minus 2x minus y minus z. By checking dimensionally by the principle of homogeneity, minus x plus z is equal to 0 because there is no any term for m here in this side. 3x plus y plus 2z is equal to 1 and minus 2x minus y minus z बराबर 0 because there is no any term for t on left hand side. Now solving for x, y, z. Solving for x, y and z. Solving for x, y and z. On solving for x, y and z, x is equal to 1 by 2, y is equal to minus 3 by 2 and z is equal to 1 by 2. So we get the value q L is equal to k g power 1 by 2, that was written in previous case, previous c minus 3 by 2 and h 1 by 2. So equation 1 becomes QL is equal to under root GH upon C GH upon CQ. This is the Planck's length. On substituting the value of GHC, G is equal to what? 6.67 into 10 to the power minus 11. H 6.63 into 10 to the power minus 34 and C 3 into 10 to the power 8 meter per second. Okay? By putting all these values in the value of Planck's length, we get QL is approximately equal to 10 to the power minus 35. So dear students, this is all about the applications of dimensional analysis. These 5 applications we have learned till now. Now in the next video, that is on tomorrow, we will do certain numericals based on this, and after that we will start error analysis. Thank you students. Have a nice day. Keep on studying. Thank you.